Hi there. Well, I'd like to start a three broadcast video journey into the mathematics of evolution. Well, why am I doing this? Well, it's an area I'm absolutely fascinated with. And please don't get scared. So many people get scared by mathematics. I'm not going to get horribly mathematical. I'm just going to show you the ideas and how mathematics helps us to understand these ideas. I'd like to help bring out the completeness of evolutionary theory. There's a lot of people who, for reasons of committed faith, don't even want to believe in evolution. And there's a lot of people who believe in evolution but don't really understand it. The the wonderful thing about evolution and the awful thing about evolution at the same time is that evolution is a very simple idea. As scientific fundamental principles go, evolution is the most understandable thing as far as a layman coming to grips with it. Evolution by natural selection, which is essentially Darwin's big idea, is such a straightforward idea when you compare it to something like quantum theory. There's a great saw about quantum theory is if you think you understand quantum theory, you don't understand quantum theory. Well, evolution isn't that way. Evolution is not an obscure, abstract, obtuse kind of principle. It's something that most people can intuitively get a really good understanding for. And in a funny sort of way, because it's that straightforward and quote unquote simple, we don't appreciate the richness of it. I remember Huxley said when he read Darwin's work, how stupid of me not to have thought of that myself. In a funny sort of way, I think people can not appreciate the depth and complexity of evolution, and that's brought out by evolutionary mathematics. And furthermore, evolutionary mathematics explains so much why things are the way they are, particularly in the behavior of animals and plants and everything else, why things do things the way they do. And as a matter of fact, although it's going to be hard for you to believe this at this point in my video presentation, it even explains why people are actually nice or altruistic to one another in social structures. It explains morality. Now, we'll get into that later by the third video, but these are pretty powerful ideas. What mathematics basically gives us is models of the world. There's actually two ways we can go about describing things that we see. One is known as a verbal model. This is where we just sort of put into words what we see and try to give the reasons for it in a structured form. So that's a verbal model. And a lot of things are explained in verbal models, particularly in sciences, not the physical sciences like physics. And physics has a tremendous amount which is explained mathematically, and there's not so much in the way of verbal modeling. In biology, in the old days, there used to be a tremendous amount of verbal models and not very much math. But the problem with verbal models is that when you make arguments, logical arguments, and they can sound very logical based on verbal structures, it's very hard to rigorously test that the logic that you're using is really complete and perfect. When you express things mathematically, the robustness of what you're expressing is absolutely total. And it's because we so tightly define what we mean when we have a mathematical terms. And what it also does is it makes our statements, our logical statements, totally testable. And if we're saying something that is that we don't really completely understand, and we have a flaw in our logic, with mathematics expressing these models, we find that flaw very, very quickly. And the other thing about mathematical models is mathematical models are much more able to show implications of the ideas that we have. Sometimes when we talk about something and we explain something in a verbal model, we don't necessarily come to a conclusion that if what we're saying is true, something else must be true. Mathematics absolutely makes these implications visible to us. So what are the ideas, the big ideas in evolutionary mathematics? Well, there's four very important concepts, and we'll go into those one at a time to build up our understanding. The four big ideas in the mathematics of evolution, and of course in evolution itself, are first population and population growth. Darwin really first had the first inklings of how evolution worked the way it did when he read the works of the economist Malthus, who had the paper in the 1800s, 1830s, on how population growth was not sustainable, that populations grew at an exponential rate, but the ability to produce food only grew at a linear rate, and eventually there was going to be one big hell of a problem in that. And what that meant was that there was going to be so much competition that some of the population that was growing could not survive. And who was going to survive? Well, that was economics, but of course that's also the basis of evolution. Then there's the idea of how populations actually grow in a continuous cycle of one generation leading to another. This actually has the same sort of mathematics as feedback systems do, and we'll be looking at that too. A third very important idea is the idea of the replication of individuals. That is, we have a system where we build another version of ourselves. That's what genetics is all about, the making of new individuals, and how we actually code that up. And when there is a structure like that, we have the basis for evolutionary replication, and we'll get into that idea too. And finally, of course, what we generally all have learned is one of the key elements of evolution, which is competition. And we always hear that in terms of survival of the fittest. In mathematical terms, the mathematics of competition is encapsulated in game theory. And there is a variety of game theory, which is evolutionary game theory, which applies itself to the situations of a population in competition, and that was work which was done by John Maynard Smith, and it's a seminal piece of work in our understanding of the mathematics of evolution. In the next video, we're going to look at the mathematical model of evolution. And the way that we're going to go about it is we're going to take a step-by-step historical tour through that mathematical model. Start with Charles Darwin and talk about the basic principles of evolution. And then look at the ideas that were about replication, which were the first mathematical ideas that came into evolutionary biology, ideas that were of major significance in proving Darwin was right. And then the beginnings of the ideas of competition, first in populations. This was done by two biologists, mathematicians, Voltaire and Lotka. And then finally we're going to round out the model to understand competition. Competition, as I said, is game theory. Game theory was created by John von Neumann, one of the most brilliant mathematicians of our century and of all time. And evolutionary game theory, which is game theory as it applies to evolution, was a creation of John Maynard Smith of Sussex University, again one of the great British evolutionary biologists of the last 30 years. And then we'll be able to discuss some of those really rather interesting concepts of why there is altruism in social animals and why we have evolved into the kinds of moral animals that we are.